Hi. In this video, I'll explain the concept of circular motion with respect to banking of tracks and a car moving on an inclined track. So you can see a purely circular motion with a center, and let's take a cross section of that track. And if we take a cross section, we can understand the banking angle. So the whole road is at an angle for certain sharp turns, and the horizontal is also shown there. So that's angle beta for now, although I will change it to angle theta in some later slides. So the same angle beta is reproduced in a number of places. Now the weight of the car is acting vertically downwards from the center of gravity as shown by mg. The road exerts a normal reaction perpendicular to the road, and that's n, shown by the yellow arrow. So you have mg and n. Now n has a vertical component and a horizontal component, and that forms the triangle up there with the same angle beta. So the vertical component is n cos beta as shown, and the horizontal component at the top of the triangle is n sin beta. N sin beta is unbalanced. There's nothing to balance it. So that is the one which provides the centripetal force to keep the car going in a circle, and you can see the orange arrow that moved from left to right. So when we have a ball rotating on a string, we are holding the string. Because we are holding the string, we are pulling on the string, so we are providing the tension force to keep the ball rotating in a circle. Here, the car is not held on a string to the center of the circular motion. The center of the circular motion, incidentally here, is shown by the vertical green line. Therefore, some other force must act to keep the car going in circular motion, and that force is n sin beta. There is nothing to balance it, so it's a net force acting towards the center of the circular track. And this force provides the centripetal acceleration too. Now, let's look at a 2D sketch. The track angle is designed so that the car does not have to depend upon friction to keep it from skidding. So for safety's sake, the n sin theta is exactly matched to the mv squared by r. mv squared by r is another way of expressing centripetal force. So when you match n sin theta with mv squared by r, the v, or the velocity of the car, is called the ideal velocity v. So at this ideal velocity, the car will not tend to slide outwards or inwards on the angled track. That's the whole meaning of matching both of them, and that's why static friction is zero. Now let's match up the free body diagram for the vertical direction. In the vertical direction, the only force acting upwards is n cos theta. The only force acting downwards is mg. Therefore, mg is equal to n cos theta. And you can also see the triangle below that shows the resolution. Now what if the actual speed of the car is slightly more than the ideal velocity? Now this is a case which we must understand carefully. The moment the velocity is greater, then the centripetal force n sin beta is not enough to hold the car to the center of the circular motion. So the car tends to move outwards, and I said tends to, I didn't say it's already started sliding. That tending motion is shown by the yellow arrow out there. Therefore, static friction immediately appears on the scene. Now if the velocity of the car is slightly less than the ideal velocity v, then the car will tend to fall inwards toward the center of the track, and therefore the friction force will act opposite the tendency of motion, and you can see the friction force going from bottom to the top, the red arrow. Therefore we must be clear about this friction force direction. Now let's get back to case 1. The speed is slightly more than the ideal speed. So the mv squared by r is more than n sin theta. And that's why the car tends to move outwards, and therefore friction is opposite to that tendency and acts at an angle downwards. Now because the friction is acting at an angle along the surface of the road, therefore we have to resolve the frictional forces also in the vertical and horizontal directions. That's easy. As you can see the triangle below, you have the FFR, the violet arrow at an angle, and its horizontal component is cos theta, FFR into cos theta, and the vertical component is FFR into sin theta. So just add them onto the car body sketch. So mg, which is acting downwards, has also got a partner f sine theta acting downwards. Therefore, you have the equation as shown on the top. Now let's get back to case 2, where the car speed is slightly less than the ideal speed. So here the car tends to fall inwards towards the center. Therefore, the frictional force will oppose that, and static friction force is shown by that arrow, which is acting above and at a slanting direction towards the top of the road. So we do the same thing that we did earlier, except the directions are different. You can see the vector diagram below. The friction force is acting at a slanting angle towards the top. Therefore, f sine theta is now vertically upwards, and the f cos theta is from right to left. This will affect our resolution, and the centripetal forces will get changed as shown here. The case 1, where the car speed was more than the ideal speed, will have centripetal force n sine theta plus f cos theta, and where the speed is slightly less than the ideal speed, it will have the centripetal force as n sine theta minus f cos theta. That's all there is to it. On the right hand side, mv actual whole squared by r will remain. Lastly, a word about the friction. The static friction force is Fs equal to mu into n. Mu is constant for tire and road surface. N is also kind of constant for a particular weight of the car, because we said n cos theta equal to mg, therefore n is equal to mg by cos theta. So if the car weight isn't changed, n will not change. Therefore, if the velocity becomes very high for the car whizzing around the track, mv squared by r will become so high that the static friction can't hold it anymore, and the car will start skidding. I hope this was useful to you. Thanks and have a great day.